Okay, so welcome back to the lecture number, the week number 29 rather, in which we have Professor Gobinda Majumder again going to give the second part of his lecture. As you know, the last week on November 2nd, he started this lecture on simulations and reconstruction, and he's going to continue on that. So over to Professor Gobinda Majumder. Gobinda, can you hear us?
I can't hear you, or now you can hear me.
Yes, I can. We can hear you now.
Yes, sir.
Just a minute. I do not know. I think there is a system. There is some issue is there. I do not know what is this problem.
But we can hear you, and can you
Okay.
share your slides? I mean, yes, yes.
Okay.
We can see your slides too.
Okay. Now let me pointer.
Pointer options above. Just one down, down. Yes.
Pointer. Okay.
Perfect.
Okay. Okay. I'm sorry. Today it is all the delayed happened. And previous day I was talking up to this level. Is there any echo?
No echo.
Okay. I was talking about this design of electromagnetic calorimeter, both from the CMS experiment and the BTEB experiment. Okay, then I stopped here. Okay, so I said that the simulation, this proton-proton collisions occurs or proton-antiproton collision occurs, we see the signal. But in reality, when this, let's say LHC experiment, not only one proton collision happen, there's a many more proton-proton collision happen. Let's say this is an example, I just put it here. In this interaction, there is an what once we call this hard interaction, large momentum particles are produced. But other than that, there is a many more collisions are there, and these are the defined collisions. So now in this interaction, not only we see the signal from this only one collision, one interaction, but more than one proton-proton interaction collision will be there. And in real experiment, let's say in a channels, if I have a signal for this one collision, this signal is supposed to be looks like this. But when there is a many collisions, signal will go like this. But also every 25 nanosecond we have an interactions. So previous 25 nanosecond also maybe some other collision, and after 25 nanosecond maybe some other collision. So there is not only one collision, what you call that at that point, but also 25 nanosecond earlier or 25 nanosecond later, there is a more collision. That's we call that out of time pileup. And if we just calculate the simple number, okay, I'm just apologizing this only one thing. This is intended for the student. So I have a many mathematical expressions. I will not go those expression in details. I keep it for the student in future. They can use this number, or if you have some question, you can ask me, I will answer. But I will not go all this explanation of this, what is this variable. From this explanation, I will get the number. I will just go through the number. I just say that on the average in LHC, we had roughly 30 collisions, and these I calculate from this luminosity times this interaction. That is the way I calculate it. And then this is the side, we see that what is the number of collisions in these LHC interactions. This varies from 5 to 70. So in the simulations, we have to simulate that in each times we have one hard collision, maybe there is another 70 collision on this point, another 70 collisions, and another 70 collision occurs. Like that way, with this sum spread, our beam is 5 centimeter apart, so this will be spread of this within this about 10 centimeters. We have another 70 collisions. These all the collisions occur nearly the same times, and also there is about another 70 collisions after 25 nanosecond, after 50 nanosecond. So all of them we have to add in digitized signals, in the electronic signals. What is this? We have to add all of them and then combine this distribution in the green line. That what we see, that will be these observed signals, observed digitized signals. So that simulation also has to be done. Then this other part, I will not go in details. Now at present day, everything is this digitized signals. So we have some preamplifier, pulse shapers, and then output signals is there. And I just say that this is a simplified form we write down. This is the detector, and that is some bias resistance will be there. And then there is some series resistance. And afterwards, we have these amplifier pulse shapers. And here, these inductance, capacitance, this may be the real, or this may be the just virtual. Means there will be real capacitor, or maybe just you have instrument and the ground. That's I call the virtual capacitors. We have those things. Combinedly, we will collect the signals, and each and every electronics component gives you the noise. So roughly, let's say in the left side, this figure I showed, with the time in our instrument, I may see there is a fluctuation of this current. We'll see because of this noise level in the different level noise. And our signal might be, this is the signal, signal shapes we say. And usually when the signal is smaller, signal to background, the signal and background is more or less superimposed. But when the signal is very, very large, okay, signal to background 20 is just only saying that signal is very, very larger, signal peak is very, very larger than this compared to the fluctuations. Then what is this ideal signal is supposed to see in the green one, that we will see because of this noise fluctuation, we will see this blue one like this. And then this is this our, we say, the current versus time. Most of the times we are bothered about this, what is the total area under this, or the total charge collected by this signal. And that is the most, that's the important things, that's correlated with this total incident energy of the particle. And then when we try to calculate, this is the charge. And typically, if I see this here also the blue line, if this is this, sorry, here is the black line, which is supposed to be the Landau distribution of this energy loss of the charged particle when go to the medium. Because of this fluctuation of this noise, this distribution will be wider. So in the simulations, we have to include these electronic noise factors also. And this simulation has to be done, and I am not much comfortable to explain all this. That's why I'm skipping this. Okay, sometimes Sotto maybe give a lectures on this. Okay, so now I have this simulation. This simulation takes an enormous time to simulate, particularly the simulation when this particle interact with the detector material. That's called the matter-particle interactions. And then all these electronics, or this electronics amplification, whatever you see, and it takes an enormous CPU time. So let's, for example, we say that in the high energy physics with the large number of simulated events, also large number, sometimes not the number. The single event simulation takes a very long time. Let, for example, do an experiment. The event simulation take a very long time for single one event, and it takes this huge CPU time. So for the different experiment, we just have certain simplified simulations. So here I just put this in general, we put the three category. We call the full simulation, which is based on the full detector GN4 simulation, or the fast simulations. Here we simplified the detector descriptions. So what I say, the full simulation, detailed geometry, particle track in the small steps, means every bending in the few micrometers, what is the bending it will calculate, detailed material interaction models, detailed emulation of the detector electronics and trigger, and then the reconstructions. But in the simplified, the fast simulation, we said the geometry may be simplified. We may not have this all the electronics in detail in the geometry, and we may have this thin material layer, reduce the multiple scattering, simple analytical material interaction instead of going in the detailed interactions, and of course electronics also. We just use this simple simulations of the electronics. So this is this one. And other thing also done is mainly for the theoreticians, or this when you have this new design, what is the expected signal we'll see. There you do not go for this any simulations. This simulation, let's say that in these simulations, I see this for the many event, I see that the distribution is come like this. So without going through any detailed simulations, I just take this simplified model. If the energy deposited signal is here, just using this functional form, I calculate this my measured energy of the signal. So that is called this a very simplified models. And if you see this timing, this is the some typical number, order of 10 seconds. Okay, this is not an exactly number, event by event of this pile up, it varies. For first sim, it may be 2 seconds. For this Delphis, it is a 0.01 second. And some number, if I just see here, is this typical number for a full GN simulation for the Atlas experiment. It takes some event, it takes a 1,000 seconds. But in this fast simulation, it takes a factor of 10, or even very fast simulation, it takes about 10 seconds. And this Delphis, it takes about less than a second. So depending on this, your physics requirement or the precision you want, you go for the different kind of simulations. But for reasonably good physics simulations or the good physics, we in general we go for the GN4 simulation where it takes the more time. Okay, just this fast sim versus full sim. Actually, if you see this any paper or anywhere, this comparison of this fast sim and full sim, and this is the simple resolutions or efficiency. This looks like very similar. This is the distributions of this sum of the energy of all the particle in CMS experiment, some sample. And here is this, what is the missing standards energy, what we see. If you see data and Monte Carlo, it more or less match. Okay. But it is known fact that it is difficult to match the tail overlap showers. That is very difficult to match with this fast sim. We cannot do it. So this is not reliable for the precision study or estimation of background for the real rare event search. Just keep this in mind. So fast sim, even though we use, but it is not very reliable. Okay. Then now in the simulations, I just say one word. I think earlier day Hariom was asking. It gives a detector signal based on the various assumptions went into it. For example, it did not predict that what is the Higgs mass. The Higgs mass is 125 GeV, and this figure was taken from this before the Higgs mass was discovered on the design phase of the CMS experiment. It was says that if the Higgs mass is 140 GeV or 200 GeV, for some scenario, what should be your signal you do expect to see? Here you will signal compared to this, when you see the same kind of signal, you have a background. And if you tune your selection criteria, then you can remove this background and here you will see your signal. So and if it is 200 GB, then you will see signal like this. So like this for the different mass, you can now in the simulation, you know what is the signal, Higgs signals, what is the TT bar, what is the ZBB. This is other physics. The signal, you tune your criteria such that you can see this your Higgs signal go better way, or usually you say that what is the signal to background in your signal. And then this is the two example, 140 and 200 GB. If the Higgs mass is varies from roughly 140 to 600 GB, then what could be your signal and what could be the background predictions? So this was predicted in the CMS, in the simulations, but now we know this is the Higgs is roughly about 125 in these regions. Okay. So here, so the simulation does not predict this result, but it says that if this is the Higgs is 125 GB, then what do we expect to see? So that's the simulation. Okay, now going to the collider simulation, because this is the IONO series talk, so I have to talk a little bit about IONO. So now let's see how we simulate this neutrino physics in IONO detector, or like any atmospheric neutrino simulations. So this is, I do not need to say, atmospheric neutrino comes, and this is this cavern. This is the guarded by this roughly 1 meter rock to avoid these all other backgrounds, charge particle background. And here is the cavern, and in the cavern we have these our ICAL detectors. Okay. Okay. So now in these simulations, we have mainly three input. What are the three inputs? These external inputs are the neutrino flux. So as these different cosmic ray particles are coming and the interaction the neutrino is produced, and as a function of this energy, what is this neutrino flux? In this distribution, this flux as a function of energy, it will even sharper fall down. It's multiplied by the e to the power e square. Okay, so this is not the true distribution, but with the multiplied. If you have the true distribution, then we might not have seen this distribution. This will be very, very smaller. Anyhow, so this is this distributions as a function of energy, and this the distributions for the different flavor of this neutrino produced in atmosphere. And in the simulation in atmosphere, we do not consider this tau neutrino because that fraction is very, very small. So we neglect completely. This is a mu types or electron type neutrino. And also if you see this as a function of cos theta as a zenith angle, how the neutrino flavor, it varies and it has an angular dependency. Also, there is a small dependency on phi also because of the geomagnetic field. Then initial cosmic ray particle landing on the Earth, that distribution is changing. So it has a depending on the phi also, the distribution vary. So usually we have a table which gives us a particular energy theta phi, how many numbers of neutrino coming on the Earth's surface per second per hour, some numbers we have. So that's we call the neutrino flux table. Then the neutrino, when it go to the medium, it interacts with the medium. And then what is the interaction cross sections? And what are the different kind of neutrino nucleon interactions? And here is this some charge current interaction process I am showing here. And there is a similarly you have the neutral current interactions for both nu mu and nu bar, similarly nu e and nu e bar. So these are this theoretical, this is this model based on this is the experimental data. We have this cross sections calculations for the different flavor of neutrino as a function of energy, and it depends also on the materials. So now third input is this, what is our detector geometry, what are the materials, that's input we have to give. So in this input, here is an example, we say that for example IONO, we give the input each and every point. This is this our coil, supposed to be coil, and this is the iron, this is the RPC detectors, and in between there is an iron. So all the detail of including electronics and substructures. So these three are the input was given. Now we come to the event simulations. So this I'm just describing this something what we have in 2015. This GENIE, this is the event generators. Many experimenters uses it, and this was this main reference for the GENIE softwares. Means main physics, and then the software has the defined manuals. So these distributions, so how it was done? It said that let's say this is our ICAL detectors. I just zoomed it here, ICAL detectors. And now just with the ICAL detectors, you take a radius RL. RL is this number, just distance from the center. This RL put greater than the any of this half of the diagonal distance. So that means the RL should be more than this from this point to this point or this point to this point inside 3 dimension. And there you have a circular surface of this radius RT. RT, the surface is this RT is chosen such a way that if on this surface anywhere particle come, it should cover the ICAL detector. The RL should not be RT should not be very small, such that some of this area from this surface, if the neutrino comes, it may not go in this area or in this area. So RT should be slightly bigger, but it should not be very large, because if it is very large, the muon coming here, muon will not interact with this our detector, so we lose the event, or that's why I say the loss of event or the more simulation time. So that's why it is optimized this RL and RT. So now, how do you simulate the physics event? So what it was done, this was the different steps was done. They randomly look at many directions. I just say the number 10 to the power 5 times. And so 10 to the power 5 times different theta and phi. I have this RL and RT. I just taken any number and then see from this I just throw a muon in it. So what I say that I take this surface, and in the surface I generated randomly a point and then just throw that muon in this direction and see this when neutrino go to the detectors, how much material is traversed. So that the things we calculate sigma time L. L is this total length, and the N is the Avogadro number, rho is the density of the material, and these numbers is related with this cross-section times this number of nucleon. So this gives you this probability. That's we calculate for all the direction 10 to the power 5 or like that. So from that we have the maximum of this variable for all these materials. When it pass through, it may be go the iron, air, glass, any direction if I just see. And obviously for our case the direction maximum will be from when it particle go from this direction to this diagonal direction. So that's my maximum probability, and that we will use for this using acceptance rejection method. And here also I just tell you that few things, what is in this green button it was written, and this was the extra software code we have to include in this GENIE official code to use in our GENIE4 in our ICAL detectors. First of all, in this that time this official GENIE code did not have this what it called this exposure time. That means if I just give an instrument and I give this cosmic neutrino flux and then say that in 1 year, how many events do you expect to see? It was not in their software. So this was included in that code. Okay. Second thing is that this neutrino flux, as I said, that it has a dependence on phi, but that time this code was written such that it can take only 2-dimensional table as a function of energy, and theta phi was not there. So 3-dimensional table was not there. So that's also we included. Third thing is that in these distributions, if I see this number of event, as I said that this flux is multiplied by this E square. That's why that's let's say that 10 GeV we see something, but if I divide it by E square, this number is very small. So if you use this standard table and calculated this number of event, the number of event in the high energy is very, very small, and that gives the statistical uncertainty. To avoid that, we change the flux table such that we can have the significant number of event even in the high energy. So these three major change was done in the code for the ICAL detectors. And then now the simulation purpose, first I say the P max. Now I choose randomly any directions, and then again I calculate this variable, and then this variable I see that, and then using the acceptance and rejection method, I can choose compute the probability where the accept or reject according to the ratio with respect to the P max. I accept the neutrino that in these directions one neutrino will interact with the detector medium. So that's first I choose the neutrino. But now within the path length, which material it will interact, that again using this sigma L Na rho for the different material, with this different material has a different sum of this, depending on that I calculate which material. Now let's say I choose the iron. Now iron, which part of the iron it will interact, again that will change total length of iron, and randomly I choose a position in the iron that will gives you this length of that will gives you this position of the interactions. Also one more thing, this I know this is this official code is the standard output of this, what are the output we see, but in ICAL we need this our input a standard format which can go for this GN4 simulation what I described earlier, but this official code did not have that options. So we included also this is the output format, and that give the directly input to the ICAL simulations. And actually all these things was described in this Pramana paper which was written by Ali. Okay, so those was these simulations we did, generated the neutrino event in this ICAL experiment, in the ICAL experiment. Now little more on this. Now in the simulation I am talking, this neutrino rate, if I calculate exact rate will be is given by, this is the expression, flux times sigma rho L, and then we integrated dl nu d cos theta d phi. And now flux is depends on this energy theta phi, cross section depends on this nu, the length depend on this which direction it will go, cos theta and phi. So this integration simple for a particular neutrino flavor. If I try to integrate, I cannot simply integrate it. Okay, so that's why you have to do this numerically, and that numerical expression what I described in the numerically, this is the total dNdt. It's just like this, and n is the total number of events. And just a minute. Okay, so this is this n is this total number of event. That's the way we simulate it. Okay. Now, as I said, this n total number of event. If the statistical simulation, if the n is more and more, you have a more and more precisions. So let's see the if I want to calculate that how many event we will see this 1 year. So dNdt I calculate in 1 year I multiply, that gives you the number. Now depending on this my initial n, the number of n, that my calculation of this event rate per year, or let's say some unit, if you see with this iteration when you increasing, this is the different symbol shows that if I had started the random seed, for one seed, if I have some number, let's say this is the 10 to the power 6 event, I may get 38.4. If I get another seed, I get 38.8. So it varies. But now if I increase that more and more statistics, it is independent of this input seed. So that gives us more and more precisions. Earlier day I was talking about this pi on calculate the value of pi, but just throwing the numbers within a square. So there also I have shown the numbers with the increase of the statistics, your accuracy is increasing. Here is also my accuracy is increasing with the statistics. Okay, so now the little more things also in the GENT, which was not in this, more in GENIE, which was not in this hadron colliders. Here The neutrino interact with this, let's say, iron. So iron has a 55 neutron and protons. So when this is the one interaction occurs, it interact with the nucleon within the quark, but then this particle will come out, it just scattered within the nucleus. So within the nucleus, many things happen. It may interactions, and there's, let's say, the nu comes, it produces mu, some other particle produce, they interact with these different nucleons and then eventually come off. Or maybe some particle is produced, it may absorb within the nucleus. Okay, so this is the way we say that this is the different particles are produced, and inside these many things are happen. And what we will see in this outside, that we have to have the calculations, but this we cannot do these calculations, theoretical calculation, we cannot do this nuclear. So we depend on the sum of the model, different experiment, what are the particles we see in the interactions. So that's we use as a model, and as time goes on, we are increasing this model better and better for the future experiment. So this is not just this my Feynman diagram, mu coming, this interaction occurs. This is even much larger things happen, and that's the simulation was put in this GENIE. And then eventually after the interaction, some particle will produce, and then there's a many particles will produce, and we have a, this is a simple tabular form, I just put it. What are the different particles produced? All the particles produced in the same place. So that's why the Vx, Vy, Vz are same. And then what are the particles? Here the nomenclature is this 14 is for this new mu, and that initially it comes that Px, Py, Pz. This is the energy three vectors of the new mu, and then when you interact, it produces this muon and some other particle. This is pi 0 photons, pi minus, pi plus, and this is again this protons. So all these particles are produced. It has a different momentum, a different component of the momentum, and this will go as an input to the my GENIE-4 simulations. Okay, so that's the simulation what I described for this INO, other than the GENIE-4, then the GENIE-4, then the digitization, electronics, those will be the remaining the same. Only these interactions of the initial particles, which is coming from the neutrino and the detector metal interaction, that is the different packages we are using. So in the simulation, only we can say, again repeating, detector simulation used to get an approximate performance of the detector, to have an approximate idea of the detector, I repeated the things, approximate idea of the detector performance, and used to optimize the detector for the physics goal, but need data to verify it. But also, this is the one warning, I just say that the GENIE-4 based Monte Carlo simulation, even I say GENIE-4 is the best compared to the first sim. Hardware, particularly hadron shower development, are fundamentally flawed, useless as a design tool. And this comment was made by the Richard Wigman, and who is the at present days, he is the best person to know the calorimeters. And I used to tell that to know this calorimeter, you have to be a nuclear physicist. Particle physicist will not be cannot be a good calorimeter expert, because what are the signal we see, it is coming from the eventually pair production of the photoelectric effect, and that is the nuclear physicist. And actually he was trained nuclear physicist, but at present he is guided all the high energy experiment for the designing of these calorimeters or these detectors. Okay, so now I switched from the simulation to the reconstruction and calibrations. Previous day I was supposed to talk up to this level. Okay, now actually I should have showed these pictures earlier, and this is my passion, or you can say that my okay, I like this picture very much. Whenever I want to give a talk, I in general, if there's a chance, I show these pictures. This is the pictures of these bubble chambers. And I would say that these pictures in the heading, I say the golden period of particle physics. in 60s, 70s. And our basic fundamental physics, Rajaji can tell more. All this particle physics is based on the result of this kind of sum of the photographic film. And this is the one of the film. And if you have the good eye from the photographic film, people can take out what is it. And now for this general purpose, also people shows that exactly what is it. It says that this side the neutrino is coming, it interacts with the medium, and the medium, this is interact with the medium, and then this is the picture is interpreted as the neutrino interact with the protons, it produces the mu minus, there is a d star and another protons, this another proton go this way, d star, it decay to the d0 pi plus, that the pi plus is the d0 pi plus, this is the pi plus, this d0 again decay to the k minus pi plus, this k minus is this, and this is the pi plus is this. But even after that we see a kink here, that was interpreted as the pion decay to the muon, and muon in the magnetic field, it goes, energy loss happen, and when it comes here, it shows that again this now curling is even smaller circle, and here it says that here muon decay to the electron and to neutrino. And also this k minus, when it comes here, again in this medium it interacts with this particle, it produced another particle called the sigma and pi plus. This is this pi plus, sigma decay to the neutron and pi minus we see the charged particle. The neutron we do not see directly, but here is the neutron is come, interact with the medium, it knock out the protons. When a proton goes to the medium, it does the ionization energy loss. So we see this proton stuff. So this is the way this particle physics experiment started, and we just described all these particles. Okay. Here keep in your mind only one more thing. Here only the signal what we see, I just showed only the sum of the charged particle. Even though in the description I said d star, d0, sigma, those are not, does not give any signal. Only sum of the particles gives you a signal, and that was the, okay, this is why you do not use this. This is the history. But now if I have to say that why I do not see this d star and d0, I say that those particles, a very short lifetime it decays. We do not see. And here is this table I just, this figure I put, different particle mass, what is this lifetime? In our experiment, we usually say that not the c tau, we say c tau, that means that if the particle go the relativistic velocity, how much the average distance is traveled before it decays. And in this case, if you see these all the particles, neutrino, electron and protons, we do not know that, we are assuming they are stable, we do not know the upper limit. Here are the some particles we see, there is a neutron, a muon, pion, kaon, whose c tau is more than 1 meters. So if they are produced, we may see some signal in the instrument, but all other particles, our lifetime is very small, and in general, we do not see those particles in the instrument. So this, even though all these particles are produced, Z, Higgs, TOF, W, all these are produced, but we only see this is the stable particles. And our, when you have our detectors, we design those detectors for the stable particles and also reconstructed those. And here is the sum of this snap. Okay, this is this illustration of this particle signal. Again, come back to this my CMS experiment. Let's say this is the CMS experiment. We have the different layers of the detectors. This is the tracking device. Then we have the electromagnetic calorimeters. Then we have these electronics. Then this is this hadron calorimeters. Then this is the superconducting solenoid. And these are the return yoke. And in between return yoke, we have this is the iron. This is the muon chambers which detect the muon signals. So now if there's a muon goes through these detectors, what will happen? Muon will start from this here, it will go through the detectors, and it will go through like this, solenoidal magnetic field in this direction and this direction is the opposite. So my curvature is also opposite. But after that, With the detectors for the muon, we mainly see this. Here is the some signal in the detectors. Here is also some signals, and also drift chamber will see the signals. Some signals will see, and that's the way we'll identify. This is, we know that this is the, when the muon goes through this, we will see this kind of a signal, and then now based on that we have to make our reconstruction algorithm by which we will determine this muon. Similarly, if it's the electron produced in the detectors and this collision point, electron will come here and it will make the electromagnetic showers in the electromagnetic calorimeters, and eventually we will see this is the signals, something in the electromagnetic calorimeters, and there is then some signals in the tracking device. Now, if I go for the charged hadrons, let's say pion or kaons, they also go within the medium, and they go this, they produce the signal, but observed signal is some of the signals here, and the large energy deposits in these calorimeters. Similarly, if you go to the neutral hadrons will go, there is no bending in the magnetic, there is no bending, it will go straight, and in general it deposits most of the energy here, but this is this neutral, so it does not show anything here. And now if I see these photons, which is the really abundant, mainly coming from the pi 0 decay, and here is also state comes and it deposits the energy in electromagnetic calorimeters. And we see only signal here in the instrument for a photons. So this is some idealistic case. If I just put all this together, an ideal muon, charged particle, neutral hadron, electron or photons, how do we see? As I said that we have only few particles which we see in the detectors, and in particle physics point of view we call this is the stable particles, roughly where lifetime is greater than 10 to the power minus 8 second. So C tau is greater than a meters. And these are these four different, I put a four different category. This is this, I put this E plus minus gamma, then this charged particle, neutral hadron, muon, and then also I put something is the neutrino. This is the, I put yellow color, this is almost invisible. So the neutrino, as a previous meeting people asked me, in the GENIE generators we use the neutrino. Interaction, some particle is produced, but cross section is so small that when this particle is produced, in this interaction we do neglect this neutrino interaction. So neutrino will just pass through. From some energy momentum conservation we calculated this, what is this neutrino directions. So those are the stable particles. As I say that gamma, electron, muon, we will see gamma, will see these electronic showers, no tracks, nothing will be here. Electron, the electronic showers with the track we'll see, and the muon will see this muon. But I said the charged particle, neutral particle, in general collider experiment, in general we do not have this one or two charged particle. It is coming as a jet. So that means initially I have a quark, and it's that fragmentation occurs. Eventually we see a jets, many particles. So this, all this gluon or the quark will see a jet. When this quark is C or bottom of charm, we will see the secondary vertex. It is slightly lifetime, it gives the secondary vertex. And all other high mass particles, it's a top decay to the mainly W and B. So we have to see the signal produce the W go to the lepton plus neutrino. Neutrino can detect from the missing energy. W decay with this lepton plus missing energy, and from that we can calculate the top W and BZ. Similarly, Z boson with this L plus L minus, or nu bar, we do not see the signal, but this is the signal, we will see the Z. So this is the way we reconstructed the fundamental particles, and then from the fundamental particles we go for this all other particles. As already I think I many times I said Z decay to 4, Higgs decay to the 4 lepton, Higgs decay to the 2 G bosons, G boson decay to the 4 leptons. So first I reconstruct lepton, then go to the G boson, then I reconstructed the Higgs. So that's the way we trace back. But our detectors, we fundamentally reconstructed these particles which you observe in the detectors. So I will try to talk about the reconstructions of these particles. Before these reconstructions, just one simple one. Usually our instrument signal we see like this, and this is some oscilloscope signal I am just showing here. And then I already shown this Q signal of the detectors, we will see something like this. Okay, so this our signals, and this I call this pedestals. When there is no signal in the instrument, we see some of them, and this is the reasonably good of the signals. So in our device, when we made or try to reconstruct, we try to see that this is the zero entry in the pedestals. Means here means I assume this is better to have this all the detectors is 100% efficient. There is no entries here. If even though there is an entry, there is a large gap between this peak and this peak, such that we can well separate it out that what will be the my signal and background. There should not be any contamination. And of course, this is the small pedestal spread. That way you can better energy resolution we can calculate. Okay, so but that this in hypothetically we'll see, but eventually then afterward what we'll see, this electronic signal, it gives the charge, or sometimes we measure the voltage, sometimes we measure the current, but most of the time it's the charge. But now the calibration when we come, that will tell that how we get from this femtocoulomb to this energy level. That's we want to measure. This is this 10 GeV, 50 GeV energy. That conversion, that's we call this our calibrations. Now, if we go to the real data, our digital electronic signal we store. So this is the kind of it. If you just raw data, if I call, if we see, you will see something like this is the kind of a signal numbers you will see. Okay, these numbers is in general. Let's say this is certainly oldest format data. This is this number, it is corresponding to some of the electronic channel. This first number is this electronic channels, and then in that channels maybe this is the 8 data watchtowers. What is the value of the digitized edge data? Okay, and this is the electronic channels, and our geometry, we have a mapping by which from the electronic channel to we know that in geometrically which point, which instrument giving you the signal. So from this mapping we can go to the geometrical positions. Okay? And that this is the digitized data. When I'm saying this is the digitized data, some hexagonal numbers. This the information such as an electronic ID. This is our signal shape, amplitude of the signals, or sometimes we see the signal shape, or sometimes we have a count. These are the defined information we stored. Okay, but now you see there's a many zeros. Okay, so zeros means that time the detector did not give any signal, or signal is very small, we neglect it. So I told you that, let for example, in the CMS now we have a more than 100 million channels. We cannot store all of this. So at present, this information was stored only for a channels where the channel signal is greater than a certain threshold. So we do not need to store this all the 00. But then this that you have to pay a price. Here I know this is this, when I'm saying that this number is this 001, I know which electronic channel I am talking. But when I am not storing other thing, then in digitized data, also I have to store the information of the electronic channels. Okay, so that's the way it was stored, and then it was recovered. Okay, so now in the summary of this, in these reconstructions, okay, I will not go in detail here. Only thing we say that we have a raw data, and then we might have to do some calibration. I will come later on the calibrations. That gives you this data information, and the same thing we are getting from the simulation also. And these two things, using that, we reconstructed the event. Reconstruction happened, and after the event reconstruction, we may get the feedback to the calibration for the next iterations. And I will go in the details how we go from this to this, and again go back for the calibration to have this better reconstruction. Okay. So in the reconstruction, basically we say that we reconstructed the charged particle or the neutral particles. We measured this energy momentum, identify the particles. And when I talk about the calibrations, it's this we are talking, this is the detector alignment. when our instrument electronics gives you the signal, this gain was right or wrong, or is there any change during this experiment? You have to see. Our gas detector, the drift velocity is it changing or not? Our time measurement, it was calibrated timing, synchronization was right or wrong, and energy scale of these detectors, again this is this energy scale, it depends on this magnitude, temperature, electric and magnetic field, and many more factors. Is it changing or not? And all these things has to be used from this real data and see this, is there any effect happening due to any one of these, and that has to go back to these again calibrations, and again you have to reconstruct. And so that's why the calibration is carried out continuously during the experiment. Okay, so now let's go to the first charged particle detections. This is the one clear example I just through the Bell experiment. We have, this is the heat point, different color is corresponding the different kind of an wire chamber, different signals. And we see this is the different signals, and it is the magnetic field. And because of the magnetic field, it bend in the different plus and minus bending different way. And now this, from the curvature, we can measure the momentum. I'll come to that point. So this is a clean, very clean, we can do very easily. This is the Bell experiment, but this is I just show a picture of old experiment. This is the JED experiment at Hera, who is discovered the gluon. And there, not only, this is the one quadrant of the detector, here only the 7 or 8 trajectories, but here many more trajectories, and there is a many overlap. So simple, just take this point and measure the feet. In this case, we cannot do it. And when you do this, usually do the feet, there is a many matrix inversion is there. And to avoid that, we cannot just start at all combinations to have the feed. We have to do something more that I will come. And then it a little more, let's say experiment. Not only these few particles, now we see the many more particles are produced. And if you see this Alice experiment, where this is the number of particles, even much larger. So the simply taking this, okay, this is the, I say that my trajectory, that means this, everything is given some signal in this instrument, in this path. So there is so many combinations. We cannot simply take the random combination and do the fit. And also all these cases, we have handled that all particles coming from the vertex. But this is not always the case. Many times, some of the new physics, where this particle, this is the cascade B, it produces, it goes certain distance. This is the C tau roughly I just put, and it produces a cascade minor, sigma minus, sigma B to sigma minus Jeff side equal to mu plus mu minus, sigma minus go to the lambda pi, lambda equal to the proton pi. This is the really signal observed in the D0 experiment, I think first. So for this, I need to reconstruct the trajectory which is coming very far from the vertex. And also, some of the track, because of the magnetic field, is just curled off. So we have to be sure that we are not counting 1, 2, 3 tracks or 4 tracks from the, I actually originate the same. So all these things have to taken care of it. So that's the way it will be more complicated. So this I will not go detail, just only saying simple. If I say that particle go from here to here in the magnetic field, it bend like this. If I have the 3 measurement A, B and C plane, now from this AC, assuming it is this just simple helical path, I can calculate what is the distance in BL. From that, I can calculate what is this momentum. Okay, that this momentum is, I can calculate from this total length and the radius of curvature. The radius of curvature is that determined through this my S and L. So basically, this is the S, this is how much is difference, L square by 2R. That's the way if I put it. Eventually, this is this my momentum when I measure. This momentum measurement, momentum I will see this is the PT. So this is the relation of this my momentum, and from that I can get the PT, a momentum of this particle in the transverse plane. And then also now you have to think this particle where it goes, It might have a multiple scattering. So multiple scattering, then it will not go to the exactly these directions. This much of bending, it may bend different way. Also, the measurement, each measurement has a certain uncertainty. So this, what is this arc curvature I see, the measured curvature might be slightly different. So we have some measurmental uncertainty. But here is this main point is, if I see this uncertainty is momentum measurement from this measurmental error, S is the Sagitta measurement sigma S, if I calculate, dpt by pt goes some proportionality factor pt by bl square. So as the momentum is going up and up, if you have to have the same kind of precision of the measurement, your length has to go with L square. That was the one of the drawback to measure the high momentum tracks, and that's the concept calorimeter come into the pictures. Okay, so here is the summary is that momentum measurement is the multiple scattering, it deteriorates the performance, and this tracking we cannot have this simple feat because our magnetic this multiple scattering are there. Also, particle when you go to the medium, it lose the ionization energy loss, so the curvature might be different. Okay, now in the static reconstruction, I say, as I told earlier, okay, I do not need to go in detail. For this, if I have to make this trajectory for all of them, there is so many combinations. I cannot go all the combinations. So it goes in the certain steps. First, we see that which is the signal above certain threshold that we consider as a trajectories. And then track say that some of the seed will start one point and then this will extrapolate it. This is the track seeding or the track building. We say that is starting from the track, we go building. This is called a track finder. And then this track finder, there is no fit is involved. So there is no inversion of the matrix. It just takes this little less time. And then when I am sure that these are this point belongs to a certain track, then I use only those points to fit the trajectories. So I reduce this track finder, reduce these combinations, and that use the fitting. And this is done in almost all the high energy physics experiment, not all the high energy physics, even neutrino physics means our ICAL, everywhere we use the same. And then I say that in the reconstruction, there might be some fake track that also you may have to remove. Okay, so now if I go this, so now just again the simplified form in the real data, here is this blue dot means this is this my measured point, we will see. This is this my observation in the data, we will see. And that using this data, we try to fit, this is the different trajectories, we will fit these different trajectories. What we say that heat along the track are given to the track fitter for parameter estimation. Parameters is the track parameters, momentum and other parameters, and the final validation of the track candidate we will have. But from the user point of view, user will not see what these hit points. User will see only this data point that this is trajectory that's will use for the physics analysis. Okay. Now let's see this. I just give a simple example of this. How we first find this, which are the hits could be a uh, possible hit point for a particular trajectory, or all these hits are there, all these signals are there. What are the combination I should choose? And this is this one simple mathematical form is called the Hawkes transformation. This is simple like an y is equal to mx plus c. I have a line in this straight line. Now, in this straight line, if there is many points I am having, now I have a many x and y point. Okay. Now, I transform this point to the line. I just write down the b is equal to minus xm plus y. Okay. Now, for a b is equal to xm minus y. So now I have a many x and y. So let's say this was an x1, y1, x2, y2. Now for x1, y1, this xy plane. If I go for this now in this parameter space, the m and b parameter space, I just write down b is equal to mx1, y1, b is equal to mx2, these two line I draw. and then they will intersect a particular point which is corresponding to M and B. Okay. So X and Y1, X and Y1, I can have any M and B. So that means I can have these many of these, any of these lines, M and B. Now if a M and B point, if I just try to see, this will be intersected in a point. So we can do this way, or in the straight line, I write down is the X cos alpha Y sin beta is equal to rho. And then if you go for this rho and alpha plane, then also for all these 5 points, it will meet a particular these 1 points. So this is this very simple point logic was used at present also many experiment we use at the initial phase. Why it is initial phase I'm saying? Now let's set one example. I say that again this is the CMS experiment. A trajectory it goes along this direction curvature. In the rho z plane it go to the straight line. Okay, this is one example of the trajectory. Now I have these two simulated event. The solid points is this. This is the black point is the signal which is really a point. This is the rho z plane. They are in this rho z plane. They are in the straight line. As I said, the rho z plane magnetic field in this only in the z direction. So on the R5 plane it will bending. This rho z plane there is no bending. So this is the rho z plane, and then this is this xy plane. This is this R5 plane. There is a curvature of the signals. And now I have some of the detectors. I may have the noise. So these are the noise points. So this is for the one event. Sorry, this is for a one event, and this is for the another event. And these two I just put that this curvature is in this direction. This is the curvature in other directions. Okay. Now let's I am having these all these points. I look for this rho z plane. I all this point. This is in the straight line. Now in the straight line, I go back to this my inverse plane, and this is the pictures I just show. Why did I makes me simple? Rho z in the cot theta and rho 0 plane. If I invert it, and these are these all these my intersect point I see. Here in this 2 point, I say that this is the one intersection point for these 2 points. When I'm going back to this MZ plane, I see the intersect point. So now here I have a many points. So I will have this NC2 combination of the intersections. And if I see the intersection points, this is in the slope and intersects. And that's if you see, this is this blue point. Those were these real signal points. And the red are this, what is this, the random noise points. And the mix out of these two, one is this really signal point, another one is this noise point. And there you'll see, you see this simply using this, I can just take this, which are the points intersects in these regions, only those as a signal point, or that corresponding to one of the tracks. Now if there is more than one tracks, then I will have a one cluster here, some other cluster in another place, that will be used for the another sequence. And this is this very simple, it works. But as I said that this is this collider experiment, it's useless mainly because I say that in the rho z plane, collider experiment rho z plane, it is resolution is very poor, and also from this we cannot get this bending, so that we cannot get this momentum of the tracks. So this was transformed little bit. We call this Hawk transformation in helical path. So as I earlier I showed, Pt is equal to 0.3 Br. So this is this radius of curvatures in this equation. If I say the R by R, phi minus phi 0, that way I can write down the equation phi is equal to phi 0 minus 0.3 B Pt by R. So this is this point. Now this is the point, each end point I have in phi, and it is I have this my radius point, and also this it goes, the radius is changing, phi is changing. So phi and radius they are changing. They are related with this my initial phi 0 and the pt of these tracks. So what I call this single stub with this coordinate r5 maps into the straight line of the track parameter q by pt by phi. So I just write down, this is the way, instead of r5 I say write down this phi 0 and pt. In this plane, this y is equal to mx plus c. So this is y, and this is this is the y. Sorry, this is my y is equal to mx plus c. I have to calculate this parameter m and c. So here is this phi 0 and pt are this my m and c. So in this plane, now if I invert it, this invert in q by pt and phi t plane, all these points they will intersect in this. Now here I know what will be this intersect point, this q by pt. So I know this is the what is the momentum. And actually this concept is going to use in future experiment in this even level 1 hardware trigger, because now you have a much and much more powerful FPGA, and then this algorithm can be incorporated there and it will be used in futures. Okay, so now I'll just go move fast. This is a track follower. This is another technique. As I said, that the magnetic field is not uniform in general. We may not use this Hawk transformation, and this is another technique. Let's say these are the hit points, and we know that interaction is here in the collider experiment. So my hits, this track should start from somewhere here. So this I call this is this different trajectories, different possible combination of these tracks. And then I try to see that this cannot be, because this my signal is supposed to come from the vertex. So I remove this. So these only remaining points are there. These are the possible trajectories. So now I am extrapolating these trajectories. And this is just an example. This trajectory, two trajectory I am going off. I see a hit. So here there may be two hits. So I may extrapolate it this way and extrapolate it this way. Here I see a signal. So I am going extrapolated this, but here I do not see anything. So I discarded it and I just go here and then just move on. Okay. So that's the way I have a one of this trajectory point. These are the points is maybe used for a one track reconstructions. And then that way I can go for these other points also. And there is many more variations of these finder algorithms. So one algorithm what we used in INO, this is we call the triplet method. Here our magnetic field is very non-uniform, and in this it changes in the different place of the different detectors. So we cannot use this any Hawk transformation or like a collider experiment. We do not know this muon is coming from here. It can come from any directions. So here we use this very flexible things. We are assuming only assumption was taken that the linear approximation that within the short distance track is almost linear. So with that concept, we say that we join these three points, signals in the RPC detectors in the three different plane, and then see these 3 points and these 3 points that are compatible or not, and we join them. Okay. So this is this very simplified form. We say that we started with this, and also bending at the end of the track cannot be included with this algorithm, but during the fitting time, we take care of it. Even we take care of this kind of a bending because of the magnetic field. Maybe particle can go like this way and then go like this. So in this initially finder point, we will have only this is this my finders. It will say these points will be there. But when we do the track fitting, during that time we may include these points and this point also in the fit. Okay. So that's the algorithm we use in this ion experiment.
Sir, can I ask question?
Yes.
Yeah, sir. Last slide. Go back.
Yeah, tell me.
No, one more back. So, no, not this slide. Go back.
A little louder. I have a little problem with the system.
Okay, sir. Go back. One more slide.
Gobinda, just go back to
Yeah.
Yes, sir. So, sir, suppose there is this muon multiple scattering. It is scattered, and you are.
No. So this is the ideal hypothesis I am talking. So this is the much more complicated things will come. What I am talking about here, this is an hypothetical idealistic case. Multiple scattering, it will miss. So it means with this algorithm, we cannot have 100% detection. The large multiple scattering, we lose that track.
Okay. Okay, sir.
Okay. Okay. So now this after the finder, now let's go to the track fitting algorithm. Okay, I'll try to finish in 5 to 6 minutes today. So track fitting algorithm. Okay, now this is my simplified form. I say that I just put one of these different layers. I see this is the signals. Okay, these hit points belong to the track. Track finder is given. Somehow let's see this many hits point. One of the track finder algorithm said these hit points belongs to a track. I am trying to fit it and extract these 5 parameters. So in the straight line, in a plane, a straight line, usually we have this 3 coordinate and the direction cosines. There we need this theta and five parameters. Now, if you want to define a parameter tracks at a particular surface, so that means this one coordinate is fixed. So you are left with the 4 remaining parameters. Now, in this track, when I am trying to fit, it is not a straight line, so it is a certain direction it is there, but it's the radius of curvature is there, that gives you the PT. So particular layer in Iono case, it is the defined plane, or if it is a, let's say, collider experiment, it's the surface of this, so the radius is fixed. So instead of 6 parameters, it required the 5 parameters to identify a trajectories. These 5 parameters was, let's say in Iono case, we use the 5 parameters in a plane. What is the coordinate x, y? What is the slope in the x and y? And q by p. But in collider experiment, it uses phi is the phi cot lambda q by p. I think I have these descriptions. So here is this phi is this my simple azimuthal angle. Cot lambda is this theta minus theta, pi minus theta. Theta is the polar angle, but also put the cot lambda. And q by p, this is this inverse with the charge sine curvatures. And also, if the different people use this d0, z0 or xy, this basically, when the track will fit, we have a fixed point. Let's say this in the collider experiment, this fixed point is this vertex, this coordinate system 0, 0, 0. So with respect to this, what is the shortest distance of the track? With respect to this, that's you define here the d0 and z0. Let's present this one example. Sine distance, the closest approach in the z axis. This is the d0. And then this z sine closest, z of sine closest approach. This is the z axis. Track is somewhere here. So let's say this is my coordinate center. And so track is going this. Then the z is 0 is this. Okay. So basically, if this is this track goes to this point, then your d0, z0 is 0, 0, and these are this my parameters will be there. So these are these 5 parameters. And now in the different experiment, why they use this defined convention, this will be clearer when I go in the next steps. Okay. Now let's say then, so from that we estimate one of this estimate one of these track parameters. Let's say for the simple curvatures, we fit it, we get this track from this point. And here I have this, when I am drawing a line, that means I have all the 5 parameters. But how do we get the 5 parameters? So one of the simplest approach is that, let's say I assume this is the starting value, I have these 5 parameters. Now, if I know the 5 parameters, when you go from this point to this point, I know the magnetic field, how much will bend, what is the ionization energy loss, how much of the energy loss will happen. Based on that, I know that extrapolated point where it will be. And then for my different initial assumptions, my extrapolated point may be slightly different. And then now we say that this is the point. M is this my measured point in this case. I may have the 2-dimensional coordinate, x and y coordinate, 2 parameters. And FP, this is the, P is this my 5 parameters. And this position at this point in measurement is depending on the function of these parameters. And from that initial parameters, I have this my measured point. Then I can have this simple definition of this chi-square, this measured point minus projected point for a particular parameters, the standard fee to use. And by minimizing this, we can calculate what is my PI. But here keep in mind, also of course here this when I put it, I have to take care of the error. This is not the least square. I have to do the chi-square by error, and also have to take care of this correlation between the measured point. If I have to do this, I am assuming this is the simple helical path, but it need not be helical path. It is a non-uniform magnetic field. So I have to do that. So what I say, that simple analytical equation of the helical path cannot be used directly because of the magnetic field is not uniform. dEdx of the charged particle, charging curvatures, dEdx of this charged particle, that will be the varying, so that gradually this my radius of curvature will change. And for all these reasons, simple analytical formula we cannot use. We have to go for the numerical approach. So this one of the numerical approach is the standard earlier what used to use called the least square feet. I will not go in detail. Only thing I say that what I write earlier, this is this my FP is this parameter I say. So let's I am assuming my P0 as a particularly for this parameter, initial parameters. P0 means when I'm saying this is my 5 parameters. For this P0, I have an extrapolated point FP0. But let's assume my true parameters is, true value is P, by assumption is P0. P minus P0 is delta P is very small. So I can have this simple Lorentz expansion. This Fp is equal to Fp0. A is the del F del P. Keep in mind, this is the matrix notation which have to come because the P is the 5 dimension and this is this higher order terms. Okay. Now, if we neglect this higher order term, then I can write down Fp is equal to Fp0 minus A dot P. And then now initially here I define this MPI square. That's the M, the Pi minus M, and this is the error matrix Pi minus M. So basically this is the chi-square. So only difference here and there is that here I expand and take this higher order term off. Okay, and this higher order term off. Now how can I take this higher order term off? Or this order has to be minimum. This higher order term should be negligible or very small. Otherwise, my assumption does not work. So this track parameter was chosen such a way that higher order term is minimum. For the different configurations, for this collider experiment, magnetic field in the z directions, and there this is this phi and cot theta. If you cot lambda, if you just go here, you cannot use this theta because collider experiment particle go in the 90 degree. That tan theta is blows up. So for all these reasons, these are different parameters so what use, but all are correlated. Eventually, you will get your track parameters px, py, pz. But during the feed, you have to take these options to neglect this higher order term, or you can say this is my approximation is more correct. That's why you took those parameters. Now from this chi-square, and now from the chi-square, again I minimize the chi-square, I will get my P minus P0 from this minimization, that this matrix equation will be written like this way. So I started with P0 and I have a measured point, and this is an A is the derivative, V is the error matrix. I have the P minus P0. So I have an one step delta P corrections, and then now again I go back to this here my P, and then again I update within the few iterations. If there is not much multiple scattering, the simple expression within 1 or 2 or 3 iterations, that gives you the 2 track parameters. So this is the simple technique was used long time earlier, let's say 1960s and 70s. Most of the people uses these techniques to calculate the parameters, And also this parameters, this is the expression that what will the error of the parameters. Okay, again I told that I will not go those in details. Okay, I think I will stop here, Satto. This is already 7:30.
So what do we do? What is your plan?
Again next week?
Okay, so you'll have to take one more class.
Okay,
Picture.
at least.
Okay, so let us do one thing. I would say that maybe you can summarize in the third lecture,
Yes.
and maybe then we will anyway take another some other lectures. Maybe you can compile the rest of the thing that you have. Maybe if required, a lecture, but a little later. But so these three we can go back and back, and then after that we'll take.
I think this is the three will go back. Yeah, next week I'll see. Yeah,
Okay.
we'll go back.
Okay. Okay. So are there any more questions from the audience? Actually, there is one slightly generic question, Govinda. I'm not sure how to teach.
Just a little louder.
There's one slightly generic question. It's not exactly on what you said, but let me still ask you. This is from YouTube.
Yes.
One from Abhinav Chaudhary. It's is it possible to test the existence of sterile neutrinos using an anti-neutrino source with almost negligible background with the help of Monte Carlo simulation code?
Sterile neutrino with anti-neutrino source.
Yes, and no background or negligible background, but with help of Monte Carlo simulation code. So it's not completely clear to me, but if you have, you understand.
Okay, no, I may not be I might not understood the question properly. Only thing I can say, let's say there's many short baseline experiment.
Yes.
They are trying to see the neutrino flux which is coming from this reactor, and there observe the signal is not matching with the predicted signals, and they were interpreted that this signal is deviating to this neutrino is oscillating to the sterile neutrino, because this oscillation length is very small. So this is what is the delta m, and 2 of this delta m we know this is not compatible with this. So this is this third delta m. So that is this another kind of neutrino. So this is the sterile neutrino. So that interpretation is there. So with this experiment, people see the sterile neutrino, interpreted the sum of the results. So if the sterile neutrino is there, reactor neutrino source, we can tell that sterile neutrino is there or not.
Okay.
I'm not sure I was the point or not.
But the question also was slightly circuitous, so I didn't quite understand. Okay. Any other questions from Zoom or otherwise?
No. Who is this question? Just
this is
tell
from
him or her to write me. I may look on and tell.
Okay. So maybe can I give your email?
Yes.
Okay. Just a second.
Yeah. You can give my email to everywhere, even in this announcement also you can put.
Okay. Just a second. Yeah, just give me a second. Okay, Gobinda, then I think there are no more questions. So we would like to thank you for a very exhaustive lecture once again today on track fitting. I mean, of course, you started with the generators and went about taking examples from INO as well as many collider experiments, switching between the suitability of different techniques for one or the other type of experiments and the kind of physics one is looking at. And we look forward to your third lecture next week. That is on 16th November at the same time at 6 o'clock on Monday. So with that, thank you very much, Gobinda. Thank you.
Okay, thanks.
Good night.
I'm sorry, actually my system, I'm not saying my system. Here I connected with both desktop and laptop. Neither of them is working